All right. Yeah, we'll see if the live demo works. But hey everyone, I'm Vimal. I'm a second-year PhD student at Carnegie Mellon University, and I'm advised by Chris Harrison. And today I'm super excited to be presenting EgoTouch, on-body touch input using AR/VR headset cameras. So augmented and virtual reality is more popular than ever, right? Especially with the Quest and Vision Pro releases from Apple and Meta. And today these headsets are mainly meant to be used at home, and they kind of look bulky, right? But this is quickly changing. They're rapidly getting smaller and sleeker. Just a few weeks ago, Meta and Snap released these new augmented reality glasses that they're working on, right? And they almost look like regular glasses, so you can totally imagine, in another 5 or 10 years, you might just be walking around with these, right? And you can augment your reality with all kinds of virtual interfaces, turn-by-turn directions, places to eat down the block, maybe even a personal AI assistant. But what about input, right? Like clearly this is a very visually rich experience, but how do we give inputs to these devices? Let me show you what's available right now. So today, if you picked up one of these headsets, they'd probably come with some kind of controllers like these. And these are great, they've got all kinds of buttons, joysticks, motion sensors, and so on, giving you really precise input. But now imagine the case of AR glasses. You're already carrying one device. You don't want to be carrying anything extra. You have to keep them you have to keep remembering to keep them charged, and you have to bring them with you, and so on. And so what if instead, you could use something like this, just hand tracking? So that's what Apple decided they wanted to do. They didn't want any controllers, right? And so that's great. You don't need to carry anything around. But then actually poking in the air like this is really inaccurate, especially for things like typing. And it's hard to use because you don't get any tactile feedback. And this person isn't even walking, right? Like imagine you're walking on the road and you're poking like this at your interface. It's just going to be really, really hard to input something. So where does this leave us, right? An ideal input combination would be to have some kind of bare hands input, so you don't need to carry anything around, while still somehow retaining tactile feedback. And so how about using your skin, right? The skin has numerous advantages. First, it's always available. You have it with you. And second, there's tactile feedback. Actually double tactile feedback. So both the touching finger and the touching surface feel the touch event, right? And finally, it's really easy to use as an input device. You've been using it your whole life, right? And you really know how to use it. Like, for example, I can touch my hands behind my back. I know exactly where I'm touching without even looking at the surface. And that's a pretty unique thing for an input device. And so these advantages essentially translate into increased speed, precision, and comfort while using on-skin interfaces. So the question really is, how do we turn your skin into a touch surface for touch input, right? And of course, this has been a very active area of research for more than a decade, including a lot of research from my advisor, Chris. And so one option is to place some kind of sensor on both arms, but this is probably the most cumbersome configuration for most consumers. Alternatively, you could just instrument one of the inputting arms with sensors. And of course, you could also instrument the input receiving arm, right? But while these prior methods show promising results, as I motivated earlier, you don't want to carry anything extra. So what if you could just have no sensors on the hands? And one way to detect touches in that case is to use cameras. Early among these efforts was OmniTouch, which uses a shoulder-worn depth camera to track and detect finger touch events. And more recently, TriPad showed that hand tracking by itself could be used to make surfaces touch sensitive, but it required calibration and did not explore the skin as a surface. Finally, Pressure Vision and later Pressure Vision++ described new deep learning-based approaches to estimate contact pressure on everyday surfaces using a desk-mounted RGB camera. But while depth cameras are promising, they're less common and often noisy, leading to inaccuracies, right? And while many of these approaches use fixed desk-mounted RGB cameras, none of them support the skin as an input surface, and more importantly, they don't use cameras that are in motion. And I just wanted to reiterate, using a camera for touch sensing is a really hard problem, right? Like think about this, in most camera locations, the camera directly can't see the spot that's being touched. And so you need to use some kind of other information to detect touches. And of course, cameras need to deal with a variety of lighting conditions, skin tones, environmental factors, and noisy sensor data. And finally, to top it all off, it's really, really hard to label data when you've actually touched your skin or not, in a way that's invisible to the camera. And so circling back, how do we turn your skin into a touch surface? And more importantly, can we do it with just the sensors that are already present on the headset? And so here we present EgoTouch, a new and practical method for detecting on-body touch input using AR/VR headset cameras. And let me try to show you a live demo. So let me just pull this up. Let's see. All right, so you should see my hands being tracked over here, right? And so this is being done with MediaPipe, which is an off-the-shelf like hand tracker. And then yeah, so when I go to touch my hand, you should see that the circle turns green, right? And that's our system detecting that there's a touch. It's only using this camera over here. This is just a regular RGB camera. We're not using depth or anything. This is already in all of the headsets that you have with you. We can detect touches on this part of the hand. We can detect them on the back side as well. On the forearm, and so on, with drags as well. And of course, we can detect touch down and touch up, and as well as different touch kind of instances, which is not possible in most prior work. Not only that, but since your skin deforms differently based on how much force you put, we can detect how much force you're putting as well. So for example, over here, you can see that the circle gets bigger and smaller depending on how hard I'm pressing, right? And this works on a variety of surfaces. And so yeah, that's my live demo. Let's see. Okay, this is gonna be challenging. Let me try to bring it back here. Okay. All right. Okay, of course it doesn't work just for me. This is some examples from demos that I was giving yesterday of different people. They were trying the touch demo and the pressure demo over here. And after the talk, I'm gonna be showing, I'll be at the poster session as well, and I can show you a live demo there as well. These are just some backup slides. Yeah, so let me give you some intuition as to why this works, right? So let's try a group experiment. Take your hand up and try to touch your skin and try to visually observe what's happening, right? So what I see over here is that you see these kind of shadows that only coalesce when your finger is touching the skin, as well as these small deformations that happen when you're touching your skin. And so that's noted over here as well. This is another backup slide. And here's how our system works, right? So like I said, the input to our system is the raw camera data, and then we track the hands with an off-the-shelf hand tracker. In this case, it's MediaPipe. But on a headset, all of these headsets have hand tracking as well, so we can just use those. And then we compute an affine transform, which converts the touching finger joints into a normalized image space so that the finger is pointing up. Of course, in this case, I've chosen the index finger, but you could choose any other finger as well, and it should have the same process. Finally, that allows us to take a really tiny crop around the fingertip, which we feed into our machine learning model, which is our custom neural network that produces touch, contact, and force simultaneously. Really quickly, this network architecture that we use is FastVIT. It's a really heavily optimized transformer that runs really efficiently on mobile hardware. And that was one of the design considerations that we made when we were trying to build this system. We want to make sure that it runs really, really quickly with really low latency. So actually over here, in this whole pipeline, the slowest step is hand tracking, and it's slow by 20 times. Right? This model runs a prediction in less than a millisecond. And finally, we can feed these predictions into an event state machine that generates regular touch, regular UI touch events like touch down, touch up, and hover. Of course, to train our models, we needed to collect a data set of people touching their skin in a variety of ways. And we wanted to analyze our system across a variety of factors, right? And so we designed our data collection to include various lighting conditions, touch types, including hovering, different touch locations on the arm, and different inputting fingers. And participants also self-reported skin tone and hair density, which we use later for evaluation. And if you remember, I said that collecting ground truth labels for the skin is not really trivial, right? Prior work has kind of used some kind of human annotation where the experimenter would manually label touch events, or they requested participants to touch certain surfaces with a certain amount of force and so on. And alternatively, you could use something like a contact mic, or maybe some kind of sensing pad, but these don't really conform to the skin really well. So instead, to annotate our ground truth, we created this custom touch sensor and force sensor, which we hid behind the user's touching finger. And then during the study, we asked participants to touch various locations on their arm with varying amounts of force in whatever way felt most natural to them, right? And like I said, this sensor is hidden from the camera's view, and that's a really important feature for a vision-based system. So here's some samples from our data set. And you can see participants were encouraged to walk around, sit down, touch the skin in whatever way felt most natural to them. And you can see a variety of skin tones, hair densities, lighting conditions, background classes, and so on. And all of these include the sensor. It's just hidden from your view. You can't see it. I'm maybe going to skip this in light of time and then go straight to results. So there's a comprehensive evaluation of our system in the paper, but just some highlights. Across all our data, we had a true positive touch detection rate of over 96% and a false positive rate of about 5%. Note that this is comparable to prior work, which either used more sensors or depth cameras and evaluated in highly constrained lab settings. And then for hover, EgoTouch could robustly detect hovering with almost like a 99% accuracy. And finally, our model was also able to estimate touching force with a mean absolute error of 6.8%, which essentially translates into a 98% accuracy for binary force classification. And across different skin tones and hair densities, this is probably a question that many people have. We didn't really notice too much of a difference in performance, which is really encouraging because this could be a major problem for vision-based systems. And similarly, across different touch locations on the hand, performance was almost the same, which is really nice to see. So of course, just like any other system, EgoTouch does have some limitations. Bony areas in the knuckles, don't provide that much skin deformation, and we noticed that that was one of the features that our model learned. So not having those would lead to less performance. And similarly, we need some kind of illumination. So this setting was kind of, I was asking people before if we could turn on the lights, but they didn't end up turning on the lights. So clearly, it was a different illumination system. But for that case, we've looked at using infrared cameras and infrared illumination, and that might be able to help as well. And of course, we still need to do a much more extensive evaluation, of different skin types, and skin tones, nail polish, rings, tattoos, and so on, to really test this to be super robust. Okay, so in summary, I presented EgoTouch, a system for detecting on-skin touch input using cameras and headsets. I showed you a lot of related work, and one of the biggest challenges with adopting all of these previous systems was that they were really impractical. They needed custom hardware that didn't exist in these headsets. But now, really, for the first time, with EgoTouch, you can simply wear a headset and run EgoTouch on it with whatever cameras are already on there and get on-skin input right out of the box without any calibration, making it really practical. And before I take questions, I just wanted to highlight some other really related work that was presented at UIST this time. Handpad, SegoType, Touch Insight, and Touchpad Anywhere. I think if you like this kind of content, you should probably check out their papers as well. And that's EgoTouch. I'm happy to take any questions now.
Two quick questions.
Hi, really great paper. I'm Daisy from Princeton University. So I have, I guess, two short questions. So one is, so the fact that you use monocular videos, there you have to rely on illumination, as you mentioned.
Yes.
So I'm curious why you didn't use like stereo depth sensing. There was a paper a few years ago that used it specifically for hand tracking. That's the first question. And secondly, what are your thoughts on the performance of the system for locational precision? Because for QWERTY keyboard, which was one of the motivation, you obviously need pretty good precision. So yeah.
Yep. That's a great question. So for hand tracking, that was not really the focus of this paper. We just wanted to use whatever is available off the shelf. So of course, hand tracking on most of these headsets anyways uses multi-view stereo to do their kind of like 3D hand tracking. So of course, we could take advantage of that. Why didn't we use multiple cameras? I think we wanted to keep it as simple as we could. Start off with just one camera and see how good or bad that was. Of course, this system can be made more robust with more cameras. They're already on most of these headsets as well. And so probably that would help. Regarding your touch precision input, that totally depends on the hand tracking performance. And so we didn't really evaluate that as a part of our system right now. Basically, over here, if you see, as long as my hands are being tracked, we can tell you if that point is being touched or not on the other side of the skin. And that can tell you whether you're typing or not or something like that. Yeah.
Thank you.
Hi. Really, thanks for a great talk. I really like this work. I especially like that you don't need extra instrumentation, right? So in the context of mixed reality, people might, in the future, the wristband form factor might even be prevalent. So if you have the camera from the from the headset, and then also extra channel from the wristband. What kind of synergetic effect you can have, and to what kind of like new things you can even sense, or like amplifying the capability?
That's a great point. Thanks for the question. So let's think about this. Like, one of the failure cases for EgoTouch, if the finger is not visible, we're not going to be able to detect if it's touching or not. But if you have a wristband on your hand, you might have an extra way of detecting touches over there. So actually, one of the kind of an inside story is that the way this project started at the beginning was that we wanted to use some kind of a contact microphone on the skin in some kind of wristband form factor to kind of listen for taps. And those work great as long as you don't move your hand around. If you move your hand around, there's like a ton of noise, and so you have to deal with that as well. So yeah, combining these two modalities would definitely help, yeah. And then we can probably have some kind of new swipe trackpad where you don't even need to look at your hand while you're walking and typing, for example, yeah.
Thank you.
Yeah, thanks.